Hi everyone, I'm Professor Sarah Rankin and I would like to welcome you to Imperial COVID-19 lockdown lessons. Today is lesson 4 and we're going to be hearing from Professor Steven Riley, Dr. Caroline Walters and Dr. Lucy Okell. And we're going to be hearing about how they've been using different approaches to model the spread of the SARS-CoV-2 virus. So, as always, please have mentimeter.com open in a web page ready for the quiz, and anyone that hasn't used this before, you don't actually need to register or sign anything for this. You just go to mentimeter.com in the web browser, and then at the top when the page opens it says enter code, and we're going to give you that code. So and then you can do the quiz for free, so just to let you know. And we've got Margarita here again, so she will be looking for your questions in the chat so that we can put some questions to these guys at the end of their presentations. So let's get started, and we'll go straight over to you, Stephen.
Thank you very much. I was just trying to figure out the slide control there. Thank you very much, Sarah. So firstly, I have to make it clear there's 3 of us here today, and we're talking about a few little bits of work from a very large effort by a large number of people. The photo here on the right shows a group of us a few years ago at one of our away days, and there have been up to, I believe, 60 or even 80 people at any one point in time within our department at Imperial actively working on these different analyses to help support the COVID-19 response, both in the UK and in many different countries around the world. And we're supported very generously by a number of different funders, especially JIDEA, the Abdul Latif Jameel Foundation, and the MRC, the Medical Research Council in the UK. So it's very important that we always acknowledge the support that lets us do the projects that I'm going to talk about today. And I'm going to try and start a little bit with a general motivation, and then I'll explain one of the kind of results that we had very early on as an example. Can I just go back one slide, please, Sam? I'm struggling with the... Thank you. So at one of these meetings, one of our outreach, we were one of our away days a few years ago, we were thinking about how we can best kind of communicate what we do in some sense when we study different pathogens and think about them. And one of the things that we remembered was these playing cards, which used to be very popular in the day of, you know, and iPads and phones are not quite so popular now. But the aim of the game here was that the cards would each have one example of a tank or a wild animal or something like that, and you would all collect the cards, and then you would try and compete against each other by saying, well, I've got the heaviest shark, or I've got the heaviest animal, or I've got the fastest animal, and then whoever had the biggest or the fastest or the highest killer rating, they would win cards off the other people, and you'd play out till the end of the game. The popular brand name was called Top Trumps, and they were great for teaching people about stats and giving you a kind of intuitive background. And they also showed how it's when you think about biological systems and you think about how we have to interact with them and possibly counter threats from those systems, there are certain key properties of elements of these systems that are much more important than others. And we kind of thought, well, that's kind of a neat way of looking at the world. And in some ways, that's a little bit like what we do. So I'm going to go for a single click now. So here's an example of some of these cards. We actually had them made and we give them out when we do outreach. And what we try to do is think about all these different pandemic threats that there might be, and think about the key characteristics of those threats. And I'm not going to go through all of them individually on the slides today, but later on you'll hear about R0, the basic reproductive number, and you'll hear about the percentage of cases that die, or the infection fatality rate. So those are examples of the type of things. And in some ways, the last 5 months for us has been about working with scientists around the world, finding the best possible data to put together the most accurate picture of this new virus, the key characteristics of the new virus that we need to know in order to be able to better combat it. So it's that's a kind of a slightly simplistic way, but it really does explain the importance of the things that we do, or the order that we do things in. So moving on to the current outbreak, this is taken from the Japan Times, which I saw through a tweet on the 15th of January. And the picture is not of Japan, the picture is of shopping, a hospital parking lot in Wuhan, or actually, sorry, that's the market in Wuhan. And the story was about the second exported case. So there had been one case already exported to Thailand, and then someone had tested positive for this new virus, and the second case was exported to Japan. They don't remember having visited a market. They had returned home to Japan a few days before this, and they'd already recovered. And the really worrying thing at that point was that we may be facing some version of SARS that may have a lower infection fatality rate, and in some sense, because it was more mild, there's a risk that it may be harder to find, and it may pose more of a problem than SARS had done those years before. And just for a couple of minutes, I'm going to take you through the very first thing that we did. And before I go into this, this forms report number 1. If you go to our website, you can look. I think we're up to about 28 or 29 reports now. And many of these have been submitted as papers or have appeared as peer-reviewed papers as well. But this is the first one. And the techniques, the computational and mathematical techniques in lots of these papers are pretty sophisticated. We try and use the best techniques available. But what I want to share with you today is the first thing that we did, which was really a pretty straightforward calculation to try and figure out what the total number of cases might have been in Wuhan at the time that these first few exported cases were being picked up. And this is the one table from that report, and the calculation that it shows on here is how, and there was another exported case the next day. So by the time we actually released this, I think the 16th or the 17th, when it was actually released, there had been 3 exported cases. So working in a small team for this first report, we saw that we managed to find data on approximately the number of international travelers leaving Wuhan each day. We made some assumptions about the total size of the population from which they would be leaving. And then we figured out from what we knew about SARS, kind of how many days we'd be able to detect them if they had been infected. Because if they traveled after they stopped being infectious, we wouldn't have seen them. And if they traveled before they turned infectious, we wouldn't have seen them. So we needed those 3 bits of information, those 3 assumptions. And then quite simply by just combining those numbers to get the probability of picking up a case as an exported case, we could reverse back to our estimate of the number of cases in Wuhan at that time, and our estimate was around 1,700. And at the time, the Chinese authorities were reporting 41, not necessarily because I hasten to add that they were hiding anything, but they reported only the cases they had tested and confirmed and were seeing as severe cases in the hospital. So we felt this was very useful at the time. And I'd highlight, but I won't go into details, we also gave really good confidence bounds, which is slightly more complicated than just the arithmetic, but we made an assumption about the distribution from which these counts would arise, and we showed even the lower bound of our confidence interval was substantially higher than current reported numbers of cases, and that was a very useful result, generated a lot of interest and a lot more attention both here internationally and within China. And I don't want to take up too much time, so I'm just going to make a few general comments, because I know part of this is not just to give results, but try and explain, give a bit of a flavour about how we do this stuff. And this is a slide I use to say, if you've got an interest in maths and computers and a passion for biology and health, then there are lots of great things that you can do. And what it will often revolve around is quite a bit of coding because that's how we do maths these days most of the time. So you'll spend, we spend quite a bit of our time looking at code, designing it, getting calculations from it. And then top right is a picture of me and members of the team in the field, because we often go out to look at where we're gathering data during non-pandemic times. And then the rest of the time is you're in meetings. And this is a picture of a few of us at a meeting in Geneva a few years ago. So the actual day-to-day life is kind of coding, visiting field sites, and then meeting with colleagues and trying to figure out what to do. I think the last few comments that I'd make, just to say that we come from a large mix of backgrounds. So you need a passion for the different elements of the type of work that we do. I did standard kind of science A levels, and then I did physics. I had a wayward couple of years as a management consultant, and then I did computer science and disease modeling. I've really enjoyed my career so far. I've been with Imperial College a lot of the time, but I also spent 6 years just after SARS working at Hong Kong University. So you do get the chance to work in different places as well. So I think that was the last of the slides I was going to share. So Sarah, should I hand back to you now?
Yeah, so if I've got this right. Oh, no, you're back to there.
I did forget, so I think I was going to do the Mentimeter. Sorry about that. Should I just move on and do the Mentimeter quiz as well to set it up for later on? Sorry, Sarah, I forgot about that coming next. So if you remember looking back at the one of the characteristics that we track for these different pathogens is the percentage of cases that die. And what I wondered, given that has been a big part of the story of COVID-19, of SARS coronavirus 2, what we've done is, hopefully, if Sam has got that up, we've set up a Mentimeter question where we'd like you, before we go on with the rest of the presentation, to think a little bit to try and answer the question, what do you think the proportion is of people who die once they've been infected with the underlying virus? You hear two things quite a lot. You hear SARS-CoV-2, and that's the name of the virus, and you often hear COVID-19, that's the name of the disease. If you actually get sick, then you're a COVID-19 patient. So Sam, at this point there, everyone's off doing their doing the Mentimeter. Do we just give them a moment to do that?
Yes, give them the moment. Do you want to go on to if you go on to the next slide, then we should be able to get the results.
Got it. Okay.
So people, everybody, just go on to your go on to menti.com and type in the code.
Okay. So we'll give. Hopefully, you have got a device to hand and you can have a go. For those, we know there are quite a few more people watching than have managed to key in at the moment, but.
So Stephen, just tell me, while we're waiting for those results, I know you're sort of a keen cyclist. Have you been managing to keep any of that up during COVID? What do you cycle on a track, or what's your sort of?
So I do. I do a bit on the. I like to do road cycling, and I've done a little bit, not much. There is a virtual road cycling thing called Zwift, which I've been doing for quite a while. And in the kind of very early days of the lockdown, when we were really encouraged not to risk kind of crashing and going to hospital, I did do quite a bit of virtual racing on Zwift, which is it's nice. It's like it's kind of like Mario Kart on a bike, but without the. But
you're actually, is that a fitness thing? You're not just doing it with your thumbs?
No, it's actually, you've got to, it measures the power from the stationary bike, feeds it into the computer, then it does a whole virtual world with other people. It's, keeps me,
do you normally race? Do you race, or do you just, is it just okay.
No, the racing's really good. It's very easy. And it's a really good workout, and you don't have to worry about crashing, which is, if any of people watching actually occasionally do race a bike, the downside there is the actual crashing. So
okay, so I think we've got a good number of people who have replied now. So
yes,
we got it right.
I think that I will leave it to Lucy to comment on later, but I think there's a lot of people in the right range there. Yeah.
Okay, so we're going to come back to that. Right, so thank you, Steve. So Steve's been spending his time in lockdown just because he wants to complete his set of top trumps. So he's just sort of here doing all these calculations so he can come up with that final top trump card for SARS-CoV-2. Right, now we're going to hear from Caroline. Now, Caroline's a mathematician, and she's also involved in modelling the spread of the virus, but she uses quite a different approach to Stephen, from what I gather. And yeah, she's not doing it through computational analysis. And actually, I'm really interested to hear from her, because in her backstory, I gathered that she did a PhD in something which is called anthropology and maths. And I'm really intrigued to find out what exactly that is. So Caroline, just tell us a little bit about you first.
Hi, thanks, Sarah. So yeah, for my A-levels, I was fairly similar to what Stephen had done. So it was maths, further maths, chemistry and psychology to me, rather than physics. And then I went on to do a maths degree at Durham Uni. And that was the first time I ever saw maths being used in any way to describe things in biology, because I did a course called mathematical biology. At the end of my degree, though, I didn't know what I wanted to do. But I saw an advert for something called a PhD in anthropology and maths, and I didn't know what anthropology was. But from my A-levels, you see that I did psychology, so I quite liked doing things about human behaviour. And actually, anthropology is kind of the study of human behaviour. So what I ended up doing for my PhD was looking at how behaviours pass from person to person, so we learn from each other. So how these behaviours spread through a population, similar to the way an infectious disease could spread through a population. So that's what I did there. And I think the key interesting thing is that the maths that I used to model the spread of human behaviour is the same maths used to model the spread of infectious diseases, which is how I moved into working in mathematical models for infectious disease spread.
Okay, so that's interesting. I mean, I'd never have thought that sort of existed as a discipline, and I think we have been sort of saying this in quite a few of the other talks we've seen people doing interdisciplinary work, but usually sort of within the sciences. So maybe maths with physics, or engineers with biologists. So it's interesting to have a sort of subject that is more, you know, social sciences rather than just straightforward sciences. So well, moving on, tell us then about, you know, how you've been approaching the COVID-19 or SARS CoV-2 infection spread.
Oh, I seem to have lost the slide control.
Okay, I think Sam's around. He's going to sort that out. So you went to Durham. You enjoyed that. What then brought you to? You came. Yeah. What brought you to London? Did you just see a job advertised and it sounded interesting?
Yeah. So first I went to Salisbury, actually.
Oh, okay.
I moved from Durham to Salisbury for a job with Public Health England because the job was advertised, and that's where it was.
Okay. And what sort of led you to coming to London then? What was the main sort of impetus for that? I think you're back on your slides. Yeah, it's interesting how people, I mean, as scientists, we move around a lot. You know, it's like anything else. You can obviously look for job adverts, and you'll see, you know, if they want a mathematician, you could end up working in many different areas. But the other great thing about being a scientist is you can work in other countries very easily. So we have, as you know, a lot of our students and people that work at Imperial are international, and ourselves, we, for example, I spent 3 years living in California in my early 20s, being a scientist and enjoying California. So yeah. So Caroline, have you managed to get control of your slides again?
Hi, yeah, apologies for that. My internet is showing that it's very unstable, so we'll see how we go.
Let's go.
I'll try and move the slide along again.
Yeah, it's a bit sluggish, I gathered.
Yeah.
Maybe just say, yeah.
Yeah, I don't seem to. Oh,
there you
here
go.
we go. So yeah, very quickly, I actually just thought I'd show people a little bit of what it meant to do research in mathematics, because that might be something that people don't understand, because we don't do experiments like you might do in the other sciences. So for my PhD, what you end up doing is you write something called a thesis, which is a really long report of all your work. And here's a little section from my thesis. And when you do it in maths, I actually didn't do my work on a computer at this time. It was all pencil and paper. And the way you write it, you end up with lots of sentences written in English, followed by equations. But what I thought might be interesting to show you all, I've highlighted some bits because they might be familiar to you from your, maybe say you're doing A levels, it might be familiar from your maths A level. So on the left hand side, I've circled the E brackets T. So that's saying E is a function of T. And the next equation down, you'll see is dE by dt. And some of you will have studied differentiation. And that's all I've done there. So it's a rate of change. And also on the very bottom row, some of you will be familiar with the integral sign and doing integration. And what I've been doing there is using integration by parts. So I really just wanted to highlight that the stuff that I learned during my A levels, I was using 8 years later doing a PhD, because that's how maths tends to work. You just learn more and more stuff and it builds on what you've learned before. Next slide, please. So I'm going to talk to you about a very important number in epidemiology, which is called the reproduction number. You might have heard about it in the news called the R number, or sorry, I think it's just, yeah, the R number. And this is a way that we can measure how a disease is spreading through a whole population. So, for example, a disease spreading through the UK. So if you see here, I've said let the reproduction number be 2. And I've taken my first infected person over on the left-hand side. And then they go and spend time with their friends and family, and we expect that they will infect 2 more people. So there is a new generation of infections which now has 2 infected people in it. Those 2 infected people, they go on to infect 2 more people, and now we have 4 infected people, and that goes on to 8 infected people. They infect 2, so we get 16, 32, and this number keeps getting bigger and bigger, and this shows that an infection is spreading and we're having an epidemic. But a thing to note about the reproduction number is that it is an average. Could I have the next slide, please? So here I've said let the reproduction number R equal 2.6, because actually there's no reason for it to equal a whole number. In reality, a person can only infect 1 other person or 2 other people or 3. You cannot infect 0.6 of a person, but we're taking an average over the whole population. What this also means is that even with our reproduction number of 2.6, we could have somebody like person A. Now they've gone on to infect 5 other people, and that's bigger than 2.6. Person B is infecting 2, and person C doesn't infect anybody, perhaps because they stayed at home when they were sick and isolated. But again, because we're taking an average, these details don't matter to us because we're looking at things on the whole population level. Next slide, please. So then we get an interesting situation where what happens if the reproduction number is less than 1? So again, if we look on the left-hand side, we've got 4 infected people. But what happens in the next generation? Well, if R is less than 1, we think that there's they won't definitely infect one more person. If R was 0.5, we could say that for every 2 infected people, we'd expect only one of them to infect one more person. So we can see here that we started with 4 infected people. That top person went on to infect nobody else, and that chain of transmission, so passing on the disease person to person, has ended because no more people get infected. Whereas the second person down, they did go on to infect somebody else, and then that person infected somebody else. But then again, we see the infection dies out and they no longer infect people. So this is what happens when an epidemic is dying out. So R less than 1 is a situation that we would like to be in with coronavirus, because that means people are not continuing to get sick. So next slide, please. So R becoming less than 1 can happen if we let the disease spread through the population and did nothing. Eventually, everybody in the population would have become sick, and people would have maybe become immune from diseases, and that's why they stop spreading. But the problem with letting that happen is that at some point, lots of people get the disease at once, and for some of those people, they get so unwell that they have to go to hospital, and some of those people will die, and we want to avoid that. And that is what's been happening in the UK with the coronavirus outbreak. So the other way of making R be below 1 is for everybody to change their behaviour. So firstly, we have lockdown. I've put here isolating. So everybody is staying at home as much as they can, and they are not seeing their friends and they are not seeing their family. Because then if you are infected, you're staying at home, so you're not meeting other people. So the number of people that you can infect, it won't be anybody if you're not meeting anybody. Therefore, the average number of people that you'll infect has got to be very small because you're not meeting anyone. It doesn't quite go to 0 though, because we can't all stay at home and not go out, because we need things like we need to go and get food. Some people have to go to work to keep the hospitals running. Some people are ill with other diseases and have to go into hospital. So that means when you do go outside, we can look at keeping our distance from people. So with coronavirus, you can catch that disease because one person who is sick breathes out, and they breathe out little droplets, and the virus lives in those droplets, and then you would breathe those in, and that is how you could get infected. But if you stand far enough away from that person, those droplets never reach you. So you can still talk to them, but from a distance. So at the UK at the moment, the advice is to stay 2 meters away from other people. The other way you could get infected is through your hands by touching things. So if you've touched something and get the virus on your hands and then you touch your face, you could become sick that way. But if everybody is washing their hands more frequently and very thoroughly, that reduces the chance of that route of transmission occurring. Next slide, please. Okay, so then we come to how do we as epidemiologists calculate this number R, and that can be quite difficult. It would be really good if we knew whether everybody in the UK right now was infected, and then we'd want to know that information tomorrow and the day after and the day after, because we'd want to know how that changed through time. But we can't know that. So we have to look at what information we can get. And one of the things we can get is the number of people who are dying from coronavirus every day. And then we assume that if every day the number of coronavirus deaths is going up, that represents the disease going up, number of people with the disease going up in the population as a whole. So if it's going down, if the deaths are going down, we then think that the number of people in the wider population with the disease is going down, and this is reflected in the number R. So we take this data of the number of deaths and we put it into our mathematical models to get an estimate for the reproduction number. But because I've said that the data we're getting doesn't actually definitely tell us what's happening, we have what we say is uncertainty around our value for R. So we never report R as a number. So we won't say R is 0.73. What you'll see is that we give a range. So I've given an example here of R could be between 0.6 and 0.9. And we could be very confident that R was in that range. And that is more useful to say the government than if we said we are 95% confident that R is 0.6 to 0.9, that is much more useful than we are 20% confident that R is in between 0.7 and 0.71, because they have a greater certainty that it is below that threshold of R being 1. I think that was my final slide there.
Great, thank you, Caroline. So really interesting how you're doing this by actual sort of what I would think of as sort of traditional sort of pen and paper maths. When you're doing it now, do you do that on a computer or do you actually?
So now that I work with infectious diseases, I do more of my work on a computer. But mainly that's because other people many years ago already did a lot of the pencil and paper maths. So what we do is we use their work and then we implement it by writing computer code.
Right, okay. Well, it's great. And thanks so much for that really clear explanation about the R number that we've been hearing a lot about in the last months. So now we're going to hear from Lucy. Lucy is a lecturer in the Department of Public Health. So all these guys are based at Imperial in the Department of Public Health. Lucy has been looking at how death rates are being calculated in the UK and around the world, and why it's important to monitor these, which I think Caroline's already touched on, because that's our sort of handle to getting into this R number. So over to you, Lucy.
Thank you. Yes, I'm just going to talk a bit about the work we've been doing since January on the coronavirus. So as you've heard from Stephen and Caroline already, there's been lots and lots of activity in the department. So in January, like everyone else, we and even December, we began to hear about the new coronavirus in Wuhan. And it soon became clear that it was spreading outside of Wuhan. So this is really to tell you a little bit of how we began to work out what the virus, how bad the virus was, how severe it was, and how much to worry about it. So we saw, of course, all of us on the news, we saw the hospitals in Wuhan having quite a devastating time, with many patients arriving with this unusual sort of pneumonia. And we began to see cases appearing outside. These were the first cases confirmed in the UK in a hotel in York that was in the news in January. So really the important question at the time was to work out how serious this virus was. We saw a lockdown being put in place in Wuhan. So we needed to know, did we also need to have a lockdown as well here? So how do we start working out how serious a virus is? So if we look at other viruses where people have done this kind of work before, so at first people said, well, maybe it's just a bit like the flu that many of us get every year. It's always circulating. Maybe it's not that different. So for seasonal flu, we think that roughly less than 0.1% of people will die if they catch the usual. If they catch the usual. If they catch the usual seasonal flu, which works out to about 1 in 1,000 or a bit less. If we think back to some of the more serious pandemics in the past, so in the last century, as you'll have heard, at the end of the First World War, there was the pandemic 1918 flu, which spread very quickly around the globe. And although it was a long time ago, there are quite good data on that, and lots of analysis has been done there. So we think that that one had a much higher death rate, so about 1% to 1.5% of people who caught it would die, and that was about obviously 1 in 100 or 1 in 150, or even a bit more than that. So that was also an unusual epidemic in that one particularly affected younger people, of course. So that was a little bit different from seasonal flu, which tends to affect older people more severely. I'll just try and move slides.
Yeah, don't worry, Lucy, it's a bit sluggish.
Yeah, okay.
Did we have the answer to the Mentimeter question, or is that coming up now?
That's coming up, yes. I'll just start talking a bit about the next slide. So early in the epidemic, quite a lot of epidemiologists around the world got sent data from Wuhan. So we had some data from hospitals in Wuhan where they were seeing patients arriving. So that was one of the first sources where we could start to work out how severe the virus was. So when we first saw the data we had, the kind of data you get is not very, it kind of sounds easy to work out how many people are dying from a virus, but actually when you see the data, you'll see why it's not as easy as it might sound. So in the data we saw in Wuhan, we found that about 10% of patients had died. About 20% of the patients they'd had recovered, but the rest of the patients were still in hospital at the time because this was very early on in the epidemic. So what does that mean in terms of the chance of dying of the virus? So we could look at that data and say, well, 10% of these patients have died, so the death rate is 10%. But of course, we don't know what's going to happen to the rest of the patients who are still in hospital. Maybe some of those may have very serious illness as well. We could just look at patients who have already got an outcome. So 30% of patients altogether have either died or recovered, and out of that 30%, 10% of those have died, and then we would get a 1/3 death rate, which would be very much higher, of course. And what other things do we need to consider? Well, I think it sounds from the Mentimeter, I think it looks like all of you know that the chance of dying of this virus is not 10% and it's not 30%. And of course, one of the reasons for that is that if we look in hospital data, we're looking at the most severe cases who do have some of the most serious outcomes, and some of them do die in the end. But of course, we now know more that there was people they had who were living in Wuhan, so they would repatriate, for example, diplomats or people working there who were from their country. And to prevent spread of infection, everybody on board those flights, on board of many of the flights, was tested. So at the time, that was the closest thing we had to a population survey telling us how many people really do have infection in a randomly selected group of people. So when we looked at those data, we found that 6 of the people on all of those flights put together were infected, and that was out of about around 600 people. So we knew that at that point in time, 1% of everyone in Wuhan was infected roughly. Of course, there was quite a small data set, really. There was only 6 people there that were infected, so it was quite a huge uncertainty at the time, because if it had been only 5 or 7 by chance, it would have made quite a difference to our calculation. And so when we factored that into account, it turned out that the final estimate of what the chances are of dying from the virus in Wuhan were about 0.66%. But there was the huge difference by age, which is something that has become much clearer over time as well. So the chance of dying was much higher in older adults. And so for that reason, we don't expect the chance of dying from the virus in the population as a whole to be exactly the same in different countries. So countries which have older populations, on average more elderly people, will have more deaths from the virus. So if we translated our estimates of the fatality rate in Wuhan to what it would be in the UK, given the higher number of older people, it turns out to be about 0.9%, so quite a bit higher, nearly 1 in 100. Next slide, please. And now, of course, the virus has spread around the world, and we're seeing huge amounts of data coming out of different countries. The numbers you'll often hear on the news being reported are the total number of deaths that have happened in each country. And what often hits the news is the number of countries that has the most deaths at a certain time. This is a graph from a very interesting website called Our World in Data, which has some really interesting things on coronavirus if you're interested in looking at more statistics on it. So you can see, as you probably hear in the news, that United States and Brazil are really high up on that graph there in terms of the total number of deaths which have happened. And this graph is showing how the number of deaths happening over time in total. And I've added the UK on there so that you can see where it is also pretty high up on the graph, together with Italy and Spain. But of course, we know that the US is a much bigger country than the UK. So is this really a fair comparison of how bad the epidemic is in different countries? And so there are other ways that you could look at these data. If we look at the next slide, I think it's coming in a minute. Yeah, so the population of the United States is more than 300 million, whereas the population of the UK is about 67 million. So even if the virus was spreading through the population in a similar way, we would expect to see more deaths in the US just because it's a bigger country. I think we're having a little bit of trouble with the connection now.
Yeah, hi Sam, can you tell us, we don't seem to be able to see Lucy's last slide. So this is where you're looking at, you're sort of, you've changed the data to look per 100,000 people, is that right?
Yes, so if we divide by the population size, if we divide the total number of deaths by the population size, we can get a little bit more of a fair comparison of countries in terms of what the death rate is per 100,000 people from the virus. So if we do it that way, then the countries are ordered in a slightly different way. So the United States is no longer at the top of the graph. In fact, the UK becomes a bit higher than the US. And countries like Belgium and Italy also very high up on that graph, because they have very large epidemics and not such big populations. The top of the graph, if you look per million, is actually San Marino, which doesn't tend to hit the news quite as much as the other countries.
And how does Brazil look?
Brazil is still high. It's just but it's underneath the UK and the US in terms of deaths per 100,000.
So what number is, sorry, because we can't see the slide, so we're just asking you, what number is the UK at the moment?
The UK is, yeah, we're on a log plot, so it's slightly difficult to read off the exact number, but it's around about roughly 700.
No, I meant, what are we the top of the chart in terms of?
Not quite. No, we're high up there. We're about approximately level with Italy, Andorra. Belgium is higher. San Marino is higher.
So I think the basic message, we haven't got the chart, but I think the basic message here is that obviously, you know, when people talk about the United States having so many cases, it makes sense because of the population size, and so you have to do some way of being able to compare properly between different countries. And so if you express the fatality rate as the number of deaths per 100,000 of the population, it's then you get quite a different picture, and actually, yeah, a worrying picture for us in the UK, because we are, you know, our death rate is high compared with other places in the world. Right, so we are having technical problems, so I'm sorry that you're not able to see us. I gather you can still hear us, is that right, Margarita? Can't hear us on YouTube. Okay, we don't know.
So should we assume that we're still recording and
yeah,
let them play back, or what's our best way to...
I think we will continue. We're going to do some questions now, because there are loads of questions. So Margarita, do you want to start picking a question? and asking whoever it is.
Yeah, sure. Thank you for the presentation. It was really nice. And it seems that a lot of people want to share their thoughts with you. So I'm going to start with Professor Riley, if that's okay for you.
Sure.
First of all, they're asking, how do we estimate the infection fatality rate?
That would probably be better for Lucy, because that's what she's covered. So do you mind if I pass that one?
Yeah, sure.
Let Lucy give an answer to that.
Yeah, so there's two things we need to know for the infection fatality rate. So one is how many deaths we've seen from the virus. And that, of course, in itself is not that easy to measure, because we need to be sure that we're testing everybody and picking up all of those people who. If we have a reasonable number, a reasonable figure on the number of deaths, we also then need to know the total number of infections that have happened. And that is probably the hardest bit, to know how many infections there really are in the community. So at the moment, there's two ways of doing that. You can either go out and test a sample of people just randomly in the community, which is what we had on those repatriation flights from Wuhan. Or you can, increasingly, we're getting more data on antibodies, which we think is a reasonable way of finding out who's had the virus recently. And that also gives us some handle on how many people have had the infection in total. So then we take the total number of deaths and divide that by the total number of people infected to get our chance of dying from the virus.
Okay, next question.
I'm sorry about it. So, do you think that the model used was based on a previous influenza model? Can that be used to estimate the behavior of a non-influenza virus? It's a really interesting question from Ronan.
Should I take that?
Yeah, go for it.
So I think there is a bit of a perception that there is one model, and we use, even just today, we've talked about kind of projects that have used lots of different, analytical techniques or models, if you like. I think the one that has been attracted a lot of publicity is a large simulation model that we used in one of the reports, that was originally coded for flu. And I think the short answer is that for certain questions, it is a very good tool to use to look at SARS-CoV-2 with the parameters adjusted accordingly. And it's a very useful tool because it's been kind of tested so much to think about flu planning. It doesn't mean we can use that model for everything, and we've only used it for a couple of hypotheses. So for the right question, I think it probably is reasonable to use models that were originally designed for another disease, as long as they're kind of we put the best possible COVID parameters into it.
Good. Professor Riley, do you think gaining herd immunity is an effective strategy for countries to use?
So that's been a controversial topic in the UK, and I think, other than a very short period of time in early March, I don't think anybody would call it a strategy. It's a consequence. So if lots of people get infected, then you will have people who are immune, at least for a period of time. Most countries, including the UK, are aggressively trying to reduce the number of people who get infected. We want as few people to be infected as is possible. We will still have some infections, and that we will accumulate small amounts of population immunity, which is herd immunity is the proportion of population are protected. So we will accumulate small amounts, but it's in no way an objective. It's a consequence, and the objective, as far as I can see, is to reduce the number of infections to keep them as small as possible.
Great. So I assume that you believe that if the government have implemented lockdown earlier, the R value would be a little bit less than it is today, or it was back in March. Is that correct?
Caroline, are you on? Are you answering that? I'm more than happy for you to jump in on that one.
Sorry, could you repeat?
Yeah, I was saying that you know, a lot of students are asking that they believe that the government should have implemented lockdown earlier, and that would be beneficial as it would reduce the R value. Is that correct? Do you believe that it will help that?
So I think in the UK, there was recently a meeting of scientists talking about the information they gave to government, and they said that according to our models, yes, if you had locked down earlier, we think it would have saved more lives, and this could have maybe meant fewer people were infected. But what you've got to remember is that the disease epidemic, it grows very, very, very quickly, okay? So I think at the time they thought maybe every 4 days the number of cases was doubling, and it gets big very quickly. So the government have to take a lot of different things into account, and they have to be careful about when they make these decisions. So whilst we can easily look back and say, yes, it might have been better had they done this a week earlier, back in March when those decisions were being made, you don't have that information. So I think, yes, if we just look at numbers, it's very easy to say, oh, you could have done it earlier and it would have affected the numbers. But I don't think that's a fair indication about whether the decisions themselves were correct.
Yeah, I agree with you. I know I'm trying to share the thoughts of our students here. So there's another interesting question. I think, Caroline, you're the best in that. It says that, do you think that the UK government is testing enough people to be able to say for sure that the R number is dropping?
I think I'll actually might pass this to Stephen because he's done some work recently on a project to do with testing. No, it's fine.
Sorry for that.
I know Stephen's done some work to do with this.
So they're all good questions. That's a really good question. It's not just the volume of testing, it's the type of testing as well. And we are involved, actually, Caroline as well, and a few others are involved in a project called REACT, where along with a kind of sister project from the Office for National Statistics, we're randomly testing people. So we're mailing out hundreds of thousands of requests for people to join our study, sending them a swab. They do a really good nose and throat swab, but they send it back to us. And then from this random sample, we can see who's got the virus and who's not. And that's really going to help us going forward to get a clearer picture. The problem with the other data is it's all driven by an individual's probability of getting tested. And that's affected by their age, where they live, their job, and loads of other things. So I think the government is making an awful lot of effort to get as much good data as they can, but it's not easy.
So Stephen, can I just butt in on that? So you were saying about you're sending out these tests. Somebody that I know said that they've received one in the post. How many tests are you sending out?
In the first round, we sent out over 160,000 tests, and we got results from 120,620. So
this is actually a good bit of citizen science, isn't it?
It really is. And anyone watching this who gets something from the REACT study from Department of Health and Imperial College, please do join in. You've got to watch the video, do the swab as well as you can, and it is supposed to sting a little bit if you get it far enough in the nose.
Yeah, I was going to say that because I know people have been saying that about doing the home testing, that actually you've got to do it. You've got to, yeah. You've got to, yeah.
Good, then that will really help.
Right. And do you have to fill out a consent form?
Yeah, no, it's research. We're helping the government, being funded by them, but it's a research project. So you receive a letter, you're asked to fill out a form online or to call a phone number, and you consent to absolutely everything, and then the swab arrives, and then you consent.
Now when you say you consent to absolutely everything, I'm
so
just, I mean, because we're all familiar with sort of spitting in a tube and sending it away to various companies which will tell us about our DNA and, you know, whether or not we're going to get this disease or that disease, or where our ancestors have come from. So tell me exactly what you're going to do with this sample, and that you're not going to be, you know, looking at our, you know, sequencing our DNA or anything.
So what we do, so we ask for consent to look for evidence of the virus in the sample that you send, and we ask for consent to, to recontact you, and whether in the future as a follow-up study, then we may ask to do subsequent things, but would recontact you before, I believe, before we ask to do any things. But we're essentially recruiting. We're asking people to both provide us with a sample and to possibly be available for being recontacted again in the future.
Yeah, so I guess, so for example, if I explain this to students, so for yesterday we were hearing about how the virus gains entry into cells through a specific protein on the surface of cells, and that's the ACE2 receptor. And so, for example, if we discovered that there were a subpopulation of people that had a slightly different sequence of their ACE2 receptor, which meant that they either were more susceptible, took up more virus, or took up less virus, the people doing these studies might want to then go back to people that had or hadn't got the virus and look at the sequence of that particular gene.
Yeah, I don't want to give you an imprecise answer, but I am there is the possibility.
There's a possibility
that we made it, and I would have to check the exact consent that we've requested.
But I think the most important thing is to know that at the moment that is absolutely not going to be happening. And I know we've got loads more questions on here. So there's a few people asking things about dexamethasone. We've heard a lot about that in the news, and we're going to have a session on the pharmacology and all the drugs in a couple of weeks, so that will be right up to date, so we'll be covering that then. And yeah, the question that came up, I can't find it now, it was about, was it Sweden or Switzerland, somewhere that has Sweden. So yeah, tell us about Sweden. They've not had a lockdown. How did they do that then?
Also, I'm happy to jump in unless, do you want me to lead off, Lucy and Caroline, or do you want to jump in? I'm seeing nodding. So the Sweden per capita death rate is actually quite high. So what they chose to do was leave it to the people to decide their degree of social distancing. And they are having a relatively, compared to other countries that have done lockdown, they're having a relatively high per capita rate of death, but the population, as you would expect, have adjusted even without the stringent direct interventions. I'm not sure many people believe that London ever had that option. It's obviously a subject of some debate, but the speed and the early, like in the global timescale, London was infected quite early, and the epidemic was doubling very aggressively. So I think had we chosen not to go for lockdown, I don't think there's any chance that the profile of the epidemic in London, especially with regard to saturating, overwhelming the health service, would have been anything like. And Sweden has very high capacity for intensive care and things like that. So it's not a straightforward story, but Sweden is a different example. And recently they have compared themselves to their kind of Nordic neighbours and said that they made a mistake. So they have far more deaths in very, very similar countries very close to them.
Wow. Okay. So there's yes, we're learning all the time, and it's been a very steep learning curve, hasn't it, through this whole sort of pandemic. And I think it is really exciting as a scientist to see that our data is being translated and we're being listened to, and it's so valuable, I guess. So thank you, Margarita, for tracking all those questions. I'd really like to say thank you to obviously our speakers, Stephen, Carolyn and Lucy, for their excellent talks today. And thanks to Sam for producing. Next week we're going to be back. We will be having another lesson at 2 o'clock, and we're going to hear from one of our scientists who's actually been spending her lockdown in one of the large labs for public health England that has set up to actually test for the virus. And she's going to be telling you about the test, well, really about the science behind the test. So how does the test actually work? And she's going to be joined actually by a nurse, and this nurse actually works as a research nurse in the same group as Stephanie. And I really wanted you to hear from her, because I think she's doing an interesting job that I think most of you will not have heard about, that sort of option or career path. So yeah, we're going to hear about research nurses. Sam's just posted to say sorry for the sort of loss of the last slides. We will be putting this up. Maybe we will ensure that that last slide goes up in the sort of revised version that we put online. Thank you all for joining us. Please fill in the survey that's in the chat at the moment, just to tell us about your give us some feedback on the session. Enjoy the rest of your day, and hope to catch up with you next week. So goodbye from all of us.